Okay, so it's time to start today's DMAT Innovation Spotlight seminar. So this is the third DMAT Innovation Spotlight seminar. And so it is my great pleasure to introduce today's speaker, Dr. Anton Anton Bolyachkin. And so let me briefly introduce his career. So at 2019, so he received a PhD from Ural Federal University. And so for a while he worked at that university. And from 2020, so he became a postdoctoral researcher at NIMS. And so today, so he will talk about, sorry, so Anton-san, could you share the slide?
Yeah, let me start sharing. Okay.
So he will talk about accelerating the development magnetic materials with digital twins. So please start. So before that, so I have an announcement. So if you have questions, so please write in the Q&A sections. And so after that, so Anton-san will answer the question. Okay, please start.
Okay, thank you, Ms. Awasan, for a kind introduction. My name is Anton. I am from NIMS, and it's my pleasure to contribute to DxMT Innovation Spotlight Seminar. So today I will talk about digital twins of magnetic materials and how they can help to develop new materials and optimize some existing ones. But first, let me introduce what are digital twins. You may have already heard about them in mass media and in different other aspects. And overall, digital twin is an accurate virtual representation of a real-world physical object, system, or any process, which we may need to optimize it to perform some testing, monitoring, or maintenance of a system in general. So it's a very general definition. And why do we need digital twins? And why they are becoming more and more important in our everyday life? There are diverse applications which are really critical. Most of them for complicated systems, such as automotive manufacturing. So if you would like to produce a car or aircraft in a very efficient way, optimize supply chain with lots of robotic lines of construction, the factory itself is a very complicated system. And to control it, to maintain it, and optimize digital twin of a factory is becoming more and more important. And actually, many companies, such as BMW, already implementing this approach. Also, you may heard about recent progress with AI and robotics. And to train the most advanced AI models right now, real data is not enough. We need also synthetic data. And the most cutting-edge robots also trained quite often on virtual space with some digital twins. That is what Tesla is doing right now. And what is especially important personally for me is Earth simulation. So we have a problem of climate change and decision making. Understanding what is going on is really critical. And making a digital twin of our Earth and all environmental processes involved is really important. And there are many others, like making smart cities, optimizing how should we distribute 5G stations across the city for the best cover with less cost, and many, many others. Even just individual buildings sometimes are so complicated that with digital twins, you can optimize power consumption of a building and its operation in general. So that is all for our daily life. And with progress in computational power, with GPU facilities, with supercomputers, it's becoming more and more relevant for our industry and improving the quality of our life. But what about material science? Do we need digital twins for materials, and why do why do we need them? And actually, they are relevant for material science as well. And if we think of a very classical problem for material science is to investigate how how correlations in these triangles are organized, how microstructure, processing conditions, and properties, physical properties of different materials relate to each other. In particular, today I will talk about magnetic materials. And considering a general audience, let me clarify. I will talk about magnetic hysteresis. When you have a material, magnetic material, which is ferromagnetic or ferrimagnetic with some long-range magnetic ordering, when you apply to demagnetized sample magnetic field, and if the field is strong enough, you reach the saturation. Then when you reverse magnetic fields, and when it's becoming zero, it's a remanence, and you need to apply negative magnetic field in order to demagnetize the sample, that is a coercivity. I will use the word coercivity and magnetic hysteresis quite a lot during this talk. And that's all. You can make it in a cycle and obtain this so-called hysteresis loop. And these properties are very sensitive to microstructure. And understanding how coercivity, remanence, and overall magnetic hysteresis loop correlate with microstructure is a quite complicated task. It's not fully addressed, and there are still questions which are not so clear at the moment. And that's why we need digital twins for magnetic materials to establish these correlations between microstructure and magnetic properties. In NIMS, we have already demonstrated this for different materials. For example, iron platinum nanogranular media, which is used for magnetic recording. And here you can see TM images of a real material, and on the right side, digital twins we constructed in order to explain very well the hysteresis loop of a real material in simulations. Another example, again, we have some understanding about microstructure of a thin film. In this case, it's based on samarium and iron. And in a model, we reconstructed this microstructure again to explain magnetic property. Another case, which I will also discuss today, is neodymium iron boron permanent magnets. In previous cases, those are thin films, but here it's a bulk material, and to construct a digital twin for a bulk material, some extra efforts are needed. So before diving deeper to these examples and talking about permanent magnets, magnetic recording media, and so on, what do we need as ultimate goal to construct a digital twin? So for any magnetic material, and any material even in general, if we consider some structural materials, not only functional materials, their functionality, their properties depends on performance at different scales. Starting from the atomic arrangements, some atomic segregations, atomic defects like dislocations, point defects, and so on, some very local interfaces, for example, with some intermediate intergranular phases, mutual orientations of the different interfaces, and so on, and going up to the scale, up to the grain size at different scales for different materials, and even larger. For example, we can observe some domain structure in magneto-optic microscopy. So you see that for real material, the properties, the performance is like a synergy starting from the atomic scale of phenomena up to the macro scale. And ideally, if we would like to construct ultimate digital twin, we should be also able to describe materials starting from the atomic arrangement, local properties, intrinsic properties, such as what is, in case of magnetic materials, what is a long-range magnetic ordering, what is magnetic anisotropy related to the crystal structure, and other intrinsic properties. And then at the atomistic level, how this is organized at the interfaces, how domain walls interact, how domain walls, for example, interact with different point defects and other crystallographic features Then we should go up to the grain size scale and be able to reproduce some magnetization reversal process in a continuous approximation. So no anymore we see any atomic arrangement, so we consider matter solid as a continuous media. And then ideally, we should be able to describe behavior of a material in a final device. If we can realize digital twins as a system of such multi-scale simulations, it would be the best realization in order to develop new devices and for new devices to tune properties of materials precisely. But today, let me mostly focus. It's really hard to realize such a multi-scale simulations and to make it precise, to call it a digital twin. Today, let me focus mostly on mesoscale level. When we need to fit this range from nanometers up to micrometers. Even just these mesoscale simulations are quite challenging. And let me start with first material and demonstrate how we can do that for neodymium iron-boron permanent magnets. How can we construct a digital twin? But first, why do we need digital twin for permanent magnets? It's already established industry. We have a huge demand for permanent magnets, and if you think where they are employed in electric vehicles and hybrid vehicles, we fully rely on neodymium iron-boron magnets, and consumption of the magnet is increasing drastically with a higher demand for such vehicles. Also, if you think about any alternative energy like green, like wind turbines, again, you need high-performance permanent magnets for generators in a quite large amount. And the need of these wind turbines is going up as well. Even some high-end devices like headphones, hard disk drives, all of them require neodymium iron-boron magnets, even though amount is smaller, but itself number of devices is pretty large. So overall, the market of permanent magnets is going up, and you see that mostly this market is occupied by high-performance neodymium iron-boron permanent magnets. And actually, these magnets do not operate at the age of their physical performance. If we consider idealized hysteresis loop for this magnet, it's in a red. And if we compare with typical sintered neodymium iron-boron magnet, you see a large discrepancy between what we can get in terms of coercivity and what we actually have. So we have a large room for improvement of the coercivity. And in order to find a way how to improve coercivity, we should look carefully what is the microstructure features in a real material which are responsible for degradation of coercivity. We should analyze what are the correlations between microstructural features and coercivity in real magnets. That's a motivation to have a digital twins even for neodymium iron-boron magnets, which are so heavily involved in our industry right now. So they still have a room for improvement. So let's have a look how typical microstructure of neodymium iron-boron magnets look like. So there are two types of magnets, sintered magnets, and you can see an example. We have different oxide grains. In this schematic visualization, it's easier to see that we have grains of the main phase, which have certain crystallographic texture. It can be slightly misaligned, but overall all see axis in one direction. At the same time, we have some secondary phases like metallic neodymium, different oxides, other secondary phases, and most importantly, between grains, we have a very thin intergranular phase. So there are different types of this phase with different chemical composition, and this very thin area is also important to describe coercivity. So we have scale of microstructural features from nanometers up to microns, which we should cover in simulations. Another type of burned magnet is hot deformed neodymium iron boron magnets. The grain size is smaller. Usually we have less variety in secondary phases, mostly metallic neodymium in triple junctions, and grain size is smaller. So it's more feasible to realize a model, to construct it in a reasonable size with reasonable statistics, but still we should also reconstruct intergranular phase besides the just granular microstructure of a magnet. So different scales are summarized here. So in terms of grain size, we have hard deformed magnets with a grain size of about hundreds of nanometers, sintered magnets with a typical grain size of about several microns, could be some melt-span neodymium iron boron magnets, and another feature is the intergranular phase, which thickness is a couple of nanometers. So these scales should be represented in the model. And from the point of view of magnetization process which is going on in the magnet, we should construct a model which should cover, starting from the nanometers, the length of exchange correlation, the length of the main wall, it's a couple of nanometers. And coercivity and magnetization process is strongly related to the main patterns we have. And this usually starting from the several nanometers up to microns, what we can observe with magneto-optic microscopy. So in order to construct a digital twin, we should cover all these scales from nanometers up to micron, and if we can, it would be nice to go even further up to the real size of magnets. So that is usually a couple of centimeters and of about that. So the only instruments so far which can cover these ranges is micromagnetic simulation. And briefly, let me introduce what is micromagnetic simulations. So magnetic phenomena has a quantum origin. And besides that, you may know that we have Maxwell equations, and usually when company design a final device, Maxwell equations and multi-physics simulations are heavily involved. So micromagnetic simulations are filling the gap between quantum physics and phenomenological Maxwell equations. So it means that micromagnetic simulations are addressing mesoscale level of describing material at the mesoscale level, and we discretize material with the finite elements, for example, with a typical mesh size of a couple of nanometers, so it's not atomistic representation. And to define what is the configuration for magnetization, we should either solve Landau-Lifshitz-Gilbert equation if we are interested in dynamic behavior, or just minimize the energy, which has different terms, starting from exchange energy, responsible for long-range magnetic ordering. We can account for anisotropic properties of each grain using magnetic crystalline anisotropy energy, and other terms like interaction with external magnetic fields and attempt of a magnet to minimize magnetic fields created in the surrounding space. So in a nutshell, that is micromagnetic simulations. And how can we construct a model of a hot deformed neodymium iron boron magnet for micromagnetic simulations? So as I said, the model should be bulk. So it should be a three-dimensional model. And one way to get microstructural data for this model is to perform so-called FIB-SEM image tomography. It means that with scanning electron microscopy, we can get one image. Then with a focused ion beam, we can polish the surface, remove its of a thickness of about 20 nanometers and get another image, polish surface again in order to remove a layer, get another image, and so on in a sequence. It gives us a series of two-dimensional images collected in such a tomographic manner. Then what we need to do is to perform segmentation of the images. At each image, we should distinguish individual grains, and we should understand the relation of one image to another. It means that we should understand that different segmented grains belong to one grain, and at which images where the end of the grain, where it starts, and so on. Nowadays, with advance in image segmentation, with neural networks, with other algorithms, it can be done very efficiently. So this step is becoming more and more affordable for very large-scale tomographic data. Then, when we have a series of segmented images, we should think how to convert this 2D data, still 2D, into a three-dimensional model. There are different ways we realize this using some point clouds, so each grain can be reproduced, considered as a point cloud. For example, I can get a sequence of points along the contour of each grain at each image and have some surface distribution of the points. Then I can consider different algorithms, for example, using support vector machine in order to define boundaries between each point cloud, and using these planes, using these borders, I can construct finally the convex shape of each grain as shown on the slide. But as I said before, it's just a grain scale of the grains. But we know that there is intergranular phase of very thin one, couple of nanometers, and we hardly can resolve it in CM data. That's why some extra efforts are needed. So if I just scale up the model, you can see that I can construct a granular microstructure with polygons, but then I should prepare and reconstruct the intergranular phase. This can be done just in algorithmic way. I can cut all the grains, and then we can implement the intergranular phase with some algorithm. Also, we can write some algorithms in order to perform regularization of the geometry. What does it mean? It means that if we have certain geometry, not necessary it will be efficiently meshed. For high quality meshed model, we should regularize it and get rid of some small elements which are less than the mesh size we are going to use. So if the mesh size of about 2 nanometers, it means that small edges, small areas with less than 2 nanometers, with area less than a couple of square nanometers, all this should be eliminated during geometry regularization. And this was implemented, and after meshing, you can see the final status. When we have the intergranular phase nicely meshed, you see that all triangles are more or less close to be equi-edges triangles. And also we have triple junctions in the system. We should keep in mind that we should realize the model as large as possible in order to have reliable statistics, in order to be able to address more complicated magnetization processes. That's why we should try to minimize the cost of the model. So if we know that magnetization process starts from the edges of the grains, we can pay more attention to finer mesh along the boundaries of the grains, close to the edges, close to the intergranular phase, and we can reduce the mesh size towards the center of the grains. This helps us to save some memory for large-scale models. And so we can implement some benchmarks to verify which mesh would be appropriate and that the scheme of saving memory is valid. So next, here now you see the large-scale final model. So tomography was collected for the area 1.5 micrometers, and inside we have of about more than 500 grains. And still, if we would like to perform micromagnetic simulations, it's quite large volume to do that. So instead, we just cut several regions with the maximum ability for our GPU computational memory, and despite that, we still have representative statistics inside each region of about 100 grains. And another important feature is that we can collect statistics for this polycrystalline structure. We can estimate what is the grain size in 3D. We can estimate the aspect ratio, how the grains are misoriented in respect to each other, in respect to the crystallographic texture axis, and so on. And the models which we prepared, the smaller models for simulations, were statistically equivalent to the large model. So finally, let's have a look what we get with this digital twin. So on the left, you see three-dimensional visualization of the model we have, and visually it's very similar to what we see in TEM data. And features which we also observe in microscopy, such as intergranular phase, they are nicely implemented into the model, and also we can tune the properties of the triple junctions, which we were taking care in microscopy as well. This model allowed us to get a lot of useful information. So the main motivation to have a digital twin is to reduce uncertainties and assumptions behind simulations. So here, since our grain size, the packing of the grains, is equivalent to what we have in microscopy, in our simulations, we can focus on what we hardly can get from experiments. We can try to address what are individual magnetic properties of the phases inside the magnet. In particular, what are magnetic properties of the very thin intergranular phase, which experimentally almost impossible to get. So for that, we tried to vary magnetic, for example, magnetization of the intergranular phase and see how coercivity is changing upon this parameter. And you can see that a combination of certain properties, for example, magnetization of the intergranular phase, we can assume some magnetization for triple junctions if they are weakly magnetic. We can nicely reproduce what we have, what the coercivity which we have at experiments. Moreover, we can confirm with other types of simulations, with other experiments that we can describe, that we can get agreement between simulations and experiments. And also what we expect from digital twins is the ability to make some decision and predictions what would be if the digital twin is transformed somehow. For example, if we have certain microstructural transformation in a model, what should we expect for coercivity? What should we expect for other magnetic properties? And that's what we implemented actually. So considering the approach we used to construct the model, we can imitate some transformations such as grain boundary diffusion. So grain boundary diffusion, it's when we cover magnet with some non-magnetic alloys with low melting point, and then during annealing, this low melting point phase can infiltrate into intergranular phase and isolate grains from each other magnetically. And that's what you see in this series of models. With gray color, it's a non-magnetic phase, and you see that gradually we can increase the volume fraction of this non-magnetic phase. Each grain is becoming more and more isolated from each other, even though still for some grains, you can see some contacts through the thin magnetic intergranular phase. In this series of models, we can control, for example, other properties and keep them unchanged. For example, the mean grain size, the aspect ratio of the grains, the distribution of easy magnetization axis. So the only what we are changing in a series of these models is the packing of the grains and their connectivity. And this allows us first to explain what is going on for experimental data when we perform grain boundary diffusion. We can again think what should be the magnetization of the intergranular phase in order to explain well experimental data. And also these simulations allow us to find a way how to improve coercivity of the magnets further. So on this x-axis is a coercivity and remanence. And if we would like to push coercivity forward, it means that first of all, we should decrease magnetization of the intergranular phase. And this gives us a hint of what we should do for experiments, how we should design experiment in order to improve coercivity further. So I hope I managed to convince you that for neodymium and iron-boron permanent magnets, digital twins are useful. They help to understand the origin of coercivity and what are the factors limiting coercivity, which we can try to improve. Another example I would like to discuss is related to permanent magnets as well. And this is so-called 112 system based on samarium iron 12 composition. It's very promising, and intrinsic properties are quite good, and we even outperforming neodymium iron-boron, but only if we have pure stoichiometry without any substitutions. But the reality is that this 112 phase can be obtained purely only in thin films. In bulk, it's very challenging to make such a system because it's unstable. Some substitutions are needed with non-magnetic elements, for example, with vanadium, with titanium, which degrades magnetization and also make it very challenging to control the phase composition and coercivity. So far, coercivity and remanence of sintered anisotropic magnets are much below what we can get in principle. And if someone can approach this goal, it would complement the market of permanent magnets, and we would not anymore see that neodymium and iron-boron magnets are the prime magnets. We can have a diversity of permanent magnets. So, as I said, in thin films, 112 system can be obtained. And that's what was done in collaboration with the Tohoku Gakuen University. You can see that in a thin film, when we have thickness of about 100 nanometer with some seed layers made of vanadium, we can realize granular microstructure. We have intergranular phase between grains, and they have very nice out-of-plane crystallographic texture. So we can have a coercivity for such a system and pretty large magnetization. And attempts to improve the intergranular phase, for example, with a grain boundary diffusion, also was applied to this system. And with the model on the left, we first try to reconstruct the top view of this system, exactly the same grain size shape and the intergranular phase with some diffusion depth of non-magnetic element silicon. And also at the bottom, we can reconstruct what are the secondary phases. For example, this red color stands for iron grains at the bottom. And in this models, we analyzed what is the role of these iron grains. They are extremely detrimental to coercivity. They serve as nucleation centers for magnetization reversal. And in the models, we can demonstrate what would be the hysteresis loop and coercivity if we first eliminate iron grains, and then if we reduce magnetization of the intergranular phase. In this case, a pretty large coercivity can be obtained, and magnetization reversal for such a system would be just switching of individual grains. It would be a perfect permanent magnet if we can realize this in bulk, and the question is how to do that. And that's where machine learning can also help. We can try to summarize all attempts in the literature about 112 system, because the system itself is known for 300 3 decays already. So there is a lot of data in the literature, and we can get useful information from it with machine learning. So the data set was collected for different compositions with different synthesis details, and the targets which we can consider are coercivity and remnants of isotropic alloys. And then we can launch optimization routine in order to optimize and obtain high coercivity and high remnants based on experimental data sets. We can train regressors to predict coercivity and remnants. And then either we can consider all possible candidates of certain composition like this, or we can launch Bayesian optimization and any other optimization routine for a much higher compositional space. It depends on what we want. And then after selecting some candidates, we can perform validation, experimental validation, and if we are satisfied, we can stop at this stage. If we are not, we are updating the dataset and repeating this cycle until convergence, until obtaining reasonable composition with good performance. And in NIMS, it's ongoing progress. You can see that on this plot with black dots, that's what we have in literature, and these orange dots, what we obtain in experiments, and we are trying to push forward and obtain performance predicted in this area. So that's what is going on right now. So to make a summary for 112 systems, we can make digital twins for some particular cases, for example, for anisotropic thin films, and understand what we should obtain in bulk in terms of phase composition, in terms of microstructural features. And then, since right now we don't have nice bulk 112 magnets, what we need optimization of existing compositions, and we can use machine learning for that. So it's like an example of how digital twins, some just advanced micromagnetic models, can be in nice combination with machine learning. Another example I would like to talk about is dedicated to neodymium iron platinum granular media, which is used for magnetic recording. So maybe you're not using as much as before hard disk drives. You could prefer some solid state memory, but still for data centers, hard disk drives are the main storage devices because they are cheap, they are reliable, and to increase further the areal density of hard disk drives, some efforts are needed. So conventional perpendicular magnetic recording approached its limit, and if we would like to move forward, we should use some energy-assisted magnetic recording, and one option is heat-assisted magnetic recording. When we have iron-platinum grains, they are very high anisotropy. With L10 order, they have very high anisotropy. It's very hard to switch their magnetization, which relates to byte, either 0 or 1. And to switch it, we should use local heating, for example, with laser. And what we expect from this iron-platinum media is a very small grain size, a very uniform grain size distribution. And it's not, if we look closely at the microstructure of individual grains, we can see some defects. Some small grains for which we cannot see some L10 ordering, some grains with crystallographic defects such as twins, some misoriented grains which 001 axis is in plane, not in out of plane direction. All these are defects, and they also detrimental to the performance of the media, and the question is how detrimental they are and how to quantify them for real media. That was the motivation for us to construct a digital twin for iron platinum media. For that, we used TEM data. So We can use top view TEM image in order to construct top view contours of each grains using segmentation, using data processing to distinguish individual contour for each grain. Then, again, it's two-dimensional data. We should have a knowledge how to make it three-dimensional. We can proceed in the way that we can take statistics from the side view. For different grains, we can analyze what is the height, what is the contour of the side contour of the grain, and we can try to find a way how to mathematically describe this shape. For example, it can be used with some Bezier curves, which are very flexible and very easy to tune. Their properties can be used for that. And then when we have a top view contour and when we can prescribe a shape profile for each grain with some statistical variation, which can be extracted from the series of side view images, we can finally, in some mathematical way, through the curvilinear extrusion of the contour, reconstruct the final shape of the grain. And then perform some regularization of the geometry, and finally mesh it. That's what was done for this media, and if you just visually compare what we observe in cross-section for the media and what we have in the model, the model is very similar to what we have in real microstructure. And also in the model, we can implement some defects. For example, you can see that some grains are split in two parts. It means that they have 1-1-1 twin inside. And we can explain the effect of these twin grains. You can see that the volume fraction of the grains with twin is increasing. We have a degradation of the hysteresis loop. So instead of being more squared, it's becoming less and less smooth in this second quadrant. Besides that, we can realize approximation of the real hysteresis loop. If we consider different parameters like magnetic anisotropic constant, volume fraction of 1-1-1 twins, volume fraction of grains with lack of L10 order, and all the rest parameters, we can launch approximation of the experimental hysteresis loops, and you can see that at certain combination we can nicely explain what we observe in experiment. And this approximation can be a way how to estimate volume fraction of different defects in real media. We can move even further. We can apply machine learning in order to collect the data set of different scenarios upon different parameters. We can simulate what should be the hysteresis loop, and then we can try to solve the inverse problem. We can consider that input is the hysteresis loop, and the problem for us to have estimations for magnetic properties and the volume fraction of nanodefects. In this case, for this, we trained neural networks, and the input data was just a sequence of points, magnetization points along the field range of interest. And when the neural networks were trained, you can see on the right that then as input data, instead of simulations, we used real experimental data. And for this experimental hysteresis loop, we have predictions for volume fraction of the defects. We can perform simulation based on these predictions and see that it's very close to what we have in experiment. And moreover, if we perform some validation of the volume fraction of defects with synchrotron XRD, we can see a nice agreement between what we predict and what we estimate from XRD. And this is very helpful to process to real iron platinum media and have some direction where to move in order to realize the goal for iron platinum hammer media. And that's not all. So for iron platinum, we can also consider some more complicated recording scenario. For example, dual layer media to increase the density further. So if we can realize one layer of iron platinum grains and the second one, and if they are isolated from each other, for example, with non-magnetic layer, we can try to realize independent configurations. For example, when we have down magnetization for the top and up magnetization for the bottom, and another option when both in one direction, both in opposite. All this gives different level for magnetization and different stray field for the sensor when we read the signal. So it gives a chance for multi-layer recording. So instead of minimizing the grain size, we can just try to make a multi-layer structure. Also, it's also quite challenging. But recently in NIMS, such a media was synthesized. So in this EDS data, you see that iron platinum grains, they are split from each other with ruthenium non-magnetic layer. Bottom layer has a very nice out of plane L10 order. So you see that 001 direction is out of plane. Top layer is less, has some other defects like in plane variance, not only out of plane orientation, but also some in plane regions. And all this, the system itself gives such a peculiar hysteresis loop. You can see such a step here, and then we have higher coercivity. So something is changing magnetization easily, and another part of the media has higher coercivity. And micromagnetic simulations were used in order to understand what are the properties of the top and bottom layer. Again, the model was realized using the statistics obtained from the TEM. We reconstructed similar grain size distribution. We reproduced in the model that in top layer, we may have some regions with in-plane variance of the L10 order. And all this allowed us to explain nicely what we have experimentally in terms of hysteresis loops. For example, for different thickness of the ruthenium layer, we were able to distinguish what are magnetic properties of the top, of the bottom layer, what is the volume fraction of in-plane variance, and so on. So to optimize such emerging new materials, micromagnetic simulations, which are based on real microstructure, which represent nicely microstructural feature, are really efficient. So now it's time to go to summary of my talk. I hope I demonstrated today that digital twins are useful for material science as well. All this was about magnetic materials, but any other functional material and structural material, establishing correlations between microstructure and physical properties and performance are really efficient if we use digital twins, and the progress of data accumulation, processing, performing high throughput experiments, and new computational facilities, all these making digital twins are more and more affordable for material science study. So far, I demonstrated that micromagnetic simulations can be performed for different systems, but ultimate goal, let me say again, to realize this multi-scale, such multi-scale models when we have ab initio simulations to address atomistic properties and up to continuous simulations to demonstrate performance of the material in a final device. And this is also a problem for other materials. So if we can realize for structural materials digital twin, including some dislocations, atomic defects, and so on, and if we can realize the model up to the continuous mesoscale level with some mechanical tests for, it can also be very beneficial to construct new materials. So that's all from my side, and most importantly, it's not a work for one person. A teamwork is really important to construct such digital twins, to collect experimental data, microscopy based on which such digital twins can be made of. So we have a large team, and you are very welcome to join us or collaborate with us. Thank you so much for your attention.
Okay, thank you very much. So thank you very much for very nice talk. And so the seminar is open for questions and comments. And Anton-san, so do you see the questions in the Q&A section? We have one question.
Yes.
Uh,
It's well known to explain Brown's paradox. It is necessary. Okay, let me just read it. It is well known that in order to explain Brown's paradox, it is necessary to take into account the properties of the magnetic surface. Did you manage to introduce the properties of the surface layer into your model? What software do you use in your modeling? So, regarding the first question, if we talk about the surface of individual grains in the magnet, yeah, we can take this into account. We can make something like partial structure for each grain and prescribe individual properties for the surface, for example, reduced magnetic anisotropy or any other feature implemented into the simulations. So I think it's feasible to do. And regarding the second question about software for simulations, for just energy minimization, we used B4X. So commercial software developed in Austria by Thomas Scheffel and his group. If we would like to do some dynamic simulations, recently we prefer using FastMac with LG equation. And regarding the first question, yeah, it's not easy to address Brown's paradox. And overall, all our attempts is to do that. And digital twins and models which pick up accurately real microstructure have a chance to do that, I think.
okay, so Anton-san, could you explain the Brown's paradox? Sorry, I do not know the Brown's paradox. So what is this?
Okay. Yeah, maybe that's what I should have started with. So Brown paradox is, if I go back to some of my slides, if you can see the slide, and that's what I was talking about. We have a cursivity for real centered magnet, and we have an expectation for cursivity like an isotropy field. And there is a large discrepancy between what we expect in theory and cursivity which we have in reality. Even though an isotropy field hardly achievable, but still, if we do even micromagnetic simulations, quite often we overestimate cursivity. And explaining why we have such an overestimation is a matter of Brown paradox. And as soon as in simulations we can reproduce cursivity, I would say the paradox would be solved.
Maybe the origin of this discrepancy is defects of
Indeed.
the DxMT.
Indeed.
And,
So
okay.
it means that we should introduce in our models defects nicely. Intergranular phase, misorientation of the grains in respect to the crystallographic texture axis, some other defects. In case of iron platinum media, also we introduced defects. Twins, disordered regions, misoriented regions. In case of 112 films, iron grains at the bottom interface, intergranular phase, those are also defects. In other words, digital twins are useful when we can carefully take care of the defects in the system and ensure statistics.
Okay, good, thank you. And so I see the Yoshikawa-san raise a hand. So, Yoshikawa-san, could you unmute yourself?
I
Okay.
This is Yoshikawa speaking. And so actually, my specialty is the building the database in the NIMS Material Data Platform Center. And so I like to know your comment about how kind of data is very, very useful for the machine learning for the developing new permanent magnet.
That's a very nice question. So it would be really useful to have the data set with intrinsic properties for various phases. For example, neodymium to iron 14 boron. Reliable list of all intrinsic properties, starting from the anisotropic constant, exchange stiffness, saturation magnetization, and so on. And for other phases, also for secondary phases. Quite often, we don't know exactly magnetic properties of some phases. That's why we should try some approximations of experimental data in order to estimate them. Such data set would be really useful for micromagnetic simulations to start to prescribe properties for individual phases. Then micromagnetic simulations can be performed and we can collect like another data set upon different microstructural features, upon different grain size. We can say with what are the magnetic properties, what is the coercivity, remnants, and so on. Maybe this data would be really useful.
I see. So your comment is, so this data set is very useful for you, not only you, but also the next generation scientists in the field in this field.
Indeed.
So I see. Okay, thank you very much.
Thank you for question.
Okay, and so I see Demura-san raised a hand. So Demura-san, could you unmute yourself?
Anton, thank you very much for your nice talk and I understand that you did a lot of dedicated works. So I have the questions on relating to topic 3. So this is very, how can I say, impressive for me because this is connecting to the device simulators, for example. So I think does it make sense to think about the possibility to pass your, how can I say, your team's output as the form of the modeling to the device manufacturers. So when you give the presentation to them, what kind of materials you've developed, you are of course explaining about the papers and also you can give the material itself. But together with these steps, I think the digital twinning model very helpful for the next manufacturer to build in their systems. So I think so. Do you have such an idea to pass your model to the device manufacturers in the digital form?
Thank you, Demura-san, for question. It's really important for us to have such cooperation with industrial partners. Unfortunately, we have, so for example, Western Digital and some other companies. So far, they were interested in some individual instruments, like software for segmentation of the images, some neural networks to process their hysteresis loops. But I think we can convince and propose a more general representation of the media in forms of a digital twin and try something more complicated. If we have large enough model, we can try simulate the actual performance of the media when we have a read-write heads, when we are passing the media and we are trying to record and read individual bits. But we should demonstrate the benefits of our digital twins comparing to the previous models.
Yeah, so actually, it is not so good idea to do everything for your side. So including the device simulations. Maybe I guess that the device manufacturer has their own device simulation systems, which is better than our material scientists. So, and the idea is that you can pass your digital modeling as it is in digital form to the next stage of the device designing tools. So the important thing is to catch up the interface problems. So if you know what kind of the digital form is necessary to adjust to their own simulation systems, I think you can make your simulation softwares inside of the materials adjusting to these interfaces. So I think in that way you can define the interfaces between them, and you concentrate to refine your model. So in that kind of a lean development is very important for fast development, I think. But anyhow, I think how can I say, digital twin modeling has a very big potential to connect with the industry side. Thank you very much.
Yes, thank you so much for your comments. We will push forward our work toward industry with industrial partners.
And one last comment is, I hope that you are going to the side of process to microstructure linkage as well.
It would be
very
really nice to do.
But thank you.
Okay, so Anton-san, so there is one question in the Q&A form. So
yes, another question from Dmitry Karpenkov. And so about the phase for this simulation, intergranular phase. So from TM data, we had EDS so we know the actual composition for the intergranular phase. Also, we did atom probe tomography, also to estimate the chemical composition of this intergranular phase. And then, based on chemical composition, we, from the literature, found the composition closest with some known magnetic properties. It was iron-enriched phase with some composition of boron and so on. So more details can be found in this paper, which is cited in the bottom right corner, about the intergranular phase, what was the composition, and which magnetic properties were prescribed to that phase.
Okay. So, do you have any other comments or questions? So if you have comments or questions, so please write in the Q&A section. If not, so it's almost time to finish the seminar. So, Anton-san, please, thank you again for very nice talk.
Yeah, thank you everyone for attending.
And so, Anton-san, so maybe you may know, so we will release, we are recording so this seminar, and so the recording video will be public in methodologies in the near future.
Yes, that's
so
great.
If you and so for the audience, so if you are interested in this seminar, and if you want to see the details again, so please see that video. So, okay. So, thank you very much again. So, I want to finish this seminar. Thank you very much.
Thanks.